Okay, so for this section, we want to talk about Newton's method. The whole idea of Newton's method is to be able to approximate the roots of a function. What I mean is, given f of x, approximate the solution to f of x equal to 0. Where is the roots of the function? In some special case, for example, quadratic equation, we already know how to find a solution. If f of x is some quadratic equation, ax squared plus bx plus c, well, the solution to f of x equal to 0 is going to be given by the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. For cubic and for quartic equation, we also have some similar formula, but we won't talk about that here. What we want to talk about is how do we approximate these if the function is not something like a quadratic. So let's take a look with a picture, with a graph. So this is some function f of x. Right here, at r, that's the root of f of x. So the whole idea behind Newton's method is going to be the following. Pick x1 close to r. Whatever that may mean, we'll talk about that in a little bit. So there's x1. Then we take the derivative of x1 and find the tangent line. Or rather, take the derivative of f of x at x1 and then find the tangent line. All right. So let me draw the tangent line. This tangent line hit the x-axis at some point, x2. And what we want to note right here is that x2 is closer to r than x1. And then we repeat. We find out where is x2 on the graph. Draw the tangent line. To get x3. And we note that here x3 is even closer to r than x2. And then we do the exact same thing over and over again. Find the tangent line, see where it hit the x-axis, and then go back and find the new tangent line. So 3. Find where the tangent line hit the x-axis and repeat step 1. Repeat step 2. So how does this actually work in terms of actually approximating these things? let's consider x1. If we take the derivative of f of x at x1, the equation of tangent line is going to be given by y minus f of x1 equal to f prime of x1. Just note that this right there is the derivative, which is also the slope of the tangent line. Then x minus x1. If we want to solve for x2, well, then we plug the point x2 back in. At x2, y is equal to 0. F prime of x1, x2 minus x1. We solve for x2. Then we solve for x2. That's going to be f prime of x1, x1 minus f of x1 divided by f prime of x1 and simplify. So we have x1 minus f of x1 over f prime of x1. Then if we want to continue to find the approximation, we would find x3, and x3 will follow in the exact same suit. x3 is now equal to x2 minus f of x2 over f prime of x2. And we can see that in the graph. Then we can actually continue on to get as close of an approximation as we like. And all of this really amount to the following. xn plus 1 is equal to xn minus f of xn over f prime of xn. Now let me go back and talk about step 1, picking an x1 that's close to R. Oftentimes we just have to take a guess as to what x1 can be and how close is that to R. But sometimes it can go wrong. For example, take the following graph. The roots is right here at R. But if we pick x1, say right here, x1 is extremely close to R. But if we try to find the derivative and the tangent line, well, the tangent line is going to give you some value of x2 that is a lot further away from R. So when this happens, we have to go back and we have to pick a new x1. And of course, if we continue to do this, we hit an x3 that's even further away from R. So when you do this, you do have to be careful about what value you choose as your x1.